following is an introduction to solving some basic rate equations or ordinary differential equations using the explicit Euler method. Engineers normally take a course on solving ODEs analytically. Here we'll use the basic technique of the explicit Euler method for solving ordinary differential equations numerically. The basic form of these equations is dy dt is some function of y and t. So normally this function will be some equation that's listed, y squared plus t e to the minus k y, etc. But it'll be in terms of y and t and any other constants. The form of the problem is that we're given the slope dy dt, so we know the function f of y comma t, which is the slope. But what we want is the actual function for y itself. We want y of t. So given the slope, find the actual function. Note that this is not the same as solving a nonlinear equation using Excel's solver function. So we're not trying to find the value of y at a given point or a single value of y. We actually want the function for y. In Excel, what that'll mean for us, especially numerically, is that we'll have a grid of time points and we'll have a corresponding array of y points. So we're going to have a column of t and a column of y, and those columns are the solution to this problem. When we plot those, we'll get a curve, and the curve itself is the solution. Now, it's not enough just to have the rate function dy dt equals f of yt. We also need an initial condition. The problem's not complete without the initial condition. So y at time 0 is equal to y naught, which is some number that we're given, like 5, for the initial condition. And this is consistent with having a rate equation when we solve this via some form of integration. We get a constant of integration. Our initial condition serves to constrain that constant of integration. And normally that's built into the solution method by starting at this initial point, and we'll see that shortly. So this is an example of the problem. So force is mass times acceleration, or the rate of change of momentum on the right hand side, is equal to the sum of external forces. So momentum is mv, the rate ddt of momentum is equal to the sum of external forces. So here, if we only consider gravitational force, we have mg. If the mass is constant, we can pull it out of the derivative, and the masses cancel, and we're left with dv dt equals g, or acceleration is gravity. With an initial condition, the initial velocity is equal to some value that is specified. This problem is simple, and we can solve it analytically. We get a linear profile for v, so if the acceleration is constant, the velocity is linear. This is an analytic solution. We're going to solve it numerically using the explicit Euler method. Now, in the explicit Euler method, we don't find y as a function of t as a continuous function at every possible point. Instead, we're only going to find the solution at discrete points. So the first thing we do is specify a grid of discrete values. This grid will be specified by a step size delta t, and then these points are labeled point 0, point 1, point 2, some generic point I, and some point I plus 1. So we know the time grid because we specify it. We know the initial condition, y0, and our goal is to find the values of y at all the other points. We do that as follows. So we take our initial rate equation, dy dt is f of yt. We replace the derivatives with deltas, so delta y over delta t, and then recognize that on the grid, delta y is just yi plus 1 minus yi, and then we evaluate the function at point I. Now, if we solve this equation in terms of yi plus 1, we get the blue equation, which is the explicit Euler formula. And this equation is a recurrence formula in the sense that we start at some known point I, and it tells us the value at the next point, I plus 1. So yi plus 1 is equal to yi plus delta t times the slope evaluated at the point at point I. We can interpret this as to get to the next point, we start at our given point I, and then we step along the slope. This is also consistent with the first two terms of a Taylor series expansion about point I. So again, if we start at point 0, then we can get to point 1 by evaluating this equation. So y0 plus delta t, f of y0 t0. Now that we have point 1, we can calculate point 2 in the similar manner. y2 is y1 plus delta t, f of y1, and so forth for some generic point I. Let's do this for a specific example. Here we have a nuclear decay problem where we have some mass or concentration of nuclear material, and the rate of change of the amount that we have is proportional to the amount that we have. So here k is a constant that we're given, and we have some initial value that we're also given. So here's the blue explicit Euler equation, and then we because our variable here is c, not y, we just change our notation to fit our specific problem, and we have c new, c next equals c previous plus delta t times the right-hand side function evaluated at point I. So in this case, our right-hand side function is minus kc. So we evaluate kc minus kc at the point I. Notice that even though we write the function in general terms as y comma t, in this case t doesn't explicitly appear, and that's just fine. Let's go ahead and solve this problem in Excel. So here we have the equation rewritten and also an algorithm with the approach to use. The first thing that we do is we write cells to hold the constants that define parts of the problem. So C0, a cell for k, and a cell for dt. And then we can put values in there. So C0, we'll let that be 1, and maybe k is 1, and dt can be 0.1. And then we need a time grid. So let's say t here and c. So our time starts at 0, and our next point is the old point plus the step size, and we'll lock that, and then we can just fill that down to create a grid of times. Now it's a good form to use to write this in terms of this cell dt, so that if we want to change our grid, we only have to change the value of this cell, and our grid auto updates for us. So that's going to be more convenient than if we just typed 0 and 0.1 and then filled that down, because then if we want to change the grid, we have to go back and explicitly calculate it. So we'll write equals the old cell plus dt and lock that, and then fill that down. Now for c, the first value is the initial condition, and all subsequent values are computed using this explicit Euler formula. So the next value is equal to the previous value plus dt, lock the cell, times minus k, lock that cell, times c previous. And we can fill that down. Now let's paint these cells yellow to indicate the initial points, and we'll make these green to indicate the cells with equations, and we fill these two down to get our solution. Now we can highlight these and plot, and we get our solution. So let's go ahead and make this be 0.2, see a little bit more of the curve. Now if we change the time step size, 0.2, we can make 0.4. You can see that we go out to longer time because we have a fixed number of steps that we're taking. If we make this step size too big, if we make it 0.5, 1.0, that's kind of the limit. If we make it any bigger than 1.1, then we start to go negative, which is not physical, and it kind of oscillates. It goes down, then up again, then down. If we make it too big, if we make it 2, we're critically oscillating, and any bigger than that, 2.1, starts to increase. If we make it 4, it literally blows up. We get huge numbers. So you always have to choose a step size with an explicit method that's smaller than the intrinsic timescale of the problem. In this case, the intrinsic timescale is 1 over k, and we can see that because just by looking at the units. So here we have dc dt, that's concentration per time, and on the right we have concentration, that means k has units of 1 over time. So our time scale would be 1 over k. Suppose k were 2, then our intrinsic time scale would be 0.5, and if we make anything, as soon as we hit 0.5 for our time step, kind of right at the limit, and anything bigger than our intrinsic time scale, 0.55, starts dropping us negative. So you always have to use a time step that's smaller than the intrinsic time scale of your problem. Okay, let's look at another example. This one would be a falling object with drag, and we want to know the velocity as a function of time, where we're given the acceleration as a function of velocity. So this problem is very similar. We start by specifying cells that have our variables. So we have v0 and g and c and t, delta t. So here g and c are constants. v0 is 0, g is gravitational acceleration 9.81, c is drag constant, and dt would be a step size 0.1. We'll put units on these: meters per second squared, inverse meter, and seconds. So then the next thing we do is to create a grid of points like before. So we make some times. 0 for the first time, and then the next time is the old time, plus dt. Lock that cell, and then we can fill that down. Then for the velocity, the first velocity is the initial condition, and the next velocity is the explicit Euler formula. So equals the old velocity plus the step size, lock it, times the function evaluated at the old point, and the function is g minus cv squared. So we g, lock it, minus c, lock it, times v old squared. And that's our explicit Euler formula. And we fill that down, and when we plot it, insert plot, we can see the behavior of this curve. Now in this case we get it's worth looking at the equation and seeing if our solution makes sense. So we have two terms, a gravitational acceleration and a drag term. At the very beginning, when the velocity is 0, there's no drag because v is 0, and we have only acceleration due to gravity, and we get a maximal slope. As we start to increase the velocity, this term becomes larger and larger and competes with g until at the very end it's the same size as g, and this whole term is 0, at which point the slope is 0, and that's what we get. It levels off to a slope of 0. We call this the terminal velocity, and we can evaluate the value here. It's 3.132. If we solve this equation for when the slope is 0, solve that for v, then v would be equal to square root of g over c, and not g over c. That cell divided by this cell, we get 3.13. So same thing. 3.132 and 3.132. Very good. So that gives us a little bit of confidence that we did it right, both by getting the answer that we expect in terms of the physics of the problem that are told to us by the equation, and also if we evaluate the steady state version of the equation, we get the expected value. So that gives us confidence that we used the explicit Euler method correctly. Another way that you can do this is by comparing to an exact solution. So in the nuclear decay problem, we have a simple linear equation, and there's a known exact solution for it. C exact, and if we write that, the exact formula is equal to C0 looks like I've named that cell anyway, F5, lock that cell, times exp of minus k, lock that cell, times t. So this is C, and then if we add that one to the plot, this red curve is the exact solution, and the blue curve is our approximate explicit Euler. And it's close. If we make the step size smaller, sure enough, we get the same value, and as we make it a little bit bigger, anyway, as the step size decreases, the approximate and exact solutions get closer. So that also is another way to have confidence that we are applying the method correctly. Let's see what happens if we add an extra, where did our PowerPoint go? If we add an extra equation. So explicit Euler method can be applied to multiple rate equations. So in this case, we have we have two functions we're solving with two rate equations, y and z. dy dt equals f of y, z, and t, and dz dt is g of y, z, and t. So in general, each of these rates can depend on all of the variables. It doesn't mean they have to, but they can, and we write it that way. So we have explicit Euler for each of these, y next, y old plus delta t f at the old point, z next equals z old plus delta t times the g function at the old point. So this is a function not to be confused with gravity. Both y and z are written in terms of the previous point. So our previous problem, the falling object problem, or it could be a raindrop or anything else, remains the same thing here, but now we have an extra rate equation for dx dt equals the velocity, so just the definition of velocity. But this allows us to find not only the velocity profile, but also the position as a function of time. So to do this, we write the explicit Euler formula for velocity, and again the explicit Euler formula for the position. X new equals x previous plus delta t times the function evaluated at the old point. In this case, the function is just v, so we evaluate v at the old point I. Let's go ahead and solve this in Excel. So again, we set up our cells, v0, x0, g, c, dt. Put values for these, 0, 0, 9.81, 1, and 0.1. Give them their units, s, 1 over meter, meters per second squared, meters, and meters per second. And then we can set up our grid. So we'll have t, 0, the next point is the old, the next point is the old point plus our step size. Lock that cell, and we can fill it down. Whoops, must have made a mistake. Equals the old point plus the step size, and fill that down. Now for the velocity, like before, we have the initial condition and then the explicit Euler formula. So the next point is equal to the old point plus step size times the slope. We step along the slope, and the slope is this function g, lock it, minus c, lock it, times the previous velocity squared. We can fill that down. And then for the position, we have the first point is x0, and the next point is equal to the first point plus dt, lock it, times the function evaluated at the old point, and the function is v old. We can fill that down. And if we plot these up, we get two curves. This first one is the velocity, and the second one is the position, and we get what we expect. So as the velocity becomes constant, the position becomes linear. If you integrate a constant, you get a linear profile. So it works like we expect. So this is a quick summary of using the explicit Euler method to solve rate equations, both single and in this case 2 equations, and it's trivial to extend it to multiple equations. We always just evaluate the right hand side in terms of the previous point. So x new depends on the previous points. V new depends on the previous points. If there were another variable z new, it would depend on all the previous points, and so forth. And that's all.